Good morning. Welcome to EMAT 2201. I'm Engineer Gilby Lagos, and today we will study symbolic mathematics using SymPy to solve advanced engineering mathematics problem. Okay. For our learning objectives, at the end of the lecture, the students will be able to solve algebra problems using symbolic mathematics in Python, or we call it SymPy, solve problems in calculus, in differential equation, and in Laplace transformation. For our first topic, we go to algebra, but before that, we need to know the first three lines of codes here. The first line is from SymPy import asterisk. It means that we are going to load module from SymPy, and then we are going to load every command because of this asterisk in your module SymPy. The next line is init printing. This will make your equation or expression really beautiful in Python SymPy. Now, to initialize your variable, we have here x equals symbols. Okay, open parentheses, close parentheses. We have single quote x. That is to define that x is a variable. Okay, now let's go to our first coding in Google Colab. First, we are going to type from SymPy. Now we are going to import asterisk. Okay, we are going to load modules. Okay, and then we are going to initialize the display of your math expression by using init printing. Then we are going to initialize our variable. This time we will make x as our variable. Okay. Now, after loading that first three lines, that is actually to load SymPy to your module. Now it's time to solve problems in algebra. So take note of these three lines of code that we have loaded a while ago. Now these three lines of code, we will use these three lines of code to solve for these problems using the variable x. Okay. Now, our first problem is to solve for the value of this fraction when x is equals to 2. And for the number 2 problem, we are going to simplify this fraction and then expand this binomial and then factor out this square of a binomial, and then we are going to solve the value of x in this quadratic equation. All right, now let's do the coding in Google Colab. Let's use Google Colab here. Okay, first, now we are going to solve for problem number 1. So in problem number 1, now we are going to write here the fraction. So we will be setting up the fraction. Okay, this is how you set up the fraction. Okay, in your numerator, we have x squared minus 3x, okay, plus 2. Now for the denominator, we have 3x minus 2. And then we have x minus 4. Now, if you will display this equation, just run this. The equation will be displayed by typing F and then run the code. Now, take note of the numerator, because later on we will substitute the value of 2 in your numerator, in the value of x, in the variable x, I mean. Now, to substitute the value 2 in your variable x, we use subs. So in here, f is your function. We have f subs. x minus a comma 2. That means you are going to substitute 2 to your x. Now, if you substitute 2, no, the value will be 0, because if you will notice, the numerator, no, is a factor of x minus 2. Same is true with 1. It will become 0 when you input the value of x, since the numerator has a factor of x minus 1. Now let's try 4. Now, if 4 is substituted to the fraction, it will give you infinite, because the denominator will become 0. So any number divided by 0 is infinite. Now, if we will use 3, now the result will be a fraction, 2, negative 2 over 7. That's how you use substitution in algebra. Now we go to the simplification of two fractions. First, now we are going to, so take note, no? This is very important. So you have to initialize, no? First, no? Only once. Now for solving for problem number 2, we are going to solve for problem number 2. So for problem number 2, we have f, or instead of f, we will be using g. So g now is equals to 1 all over x minus 2. We will set up the fraction, plus 4 all over x minus 5. And then let's try to display it by typing g. So let's try to display it first. G, then simplify. Okay. Let's just simplify. G simplify. Now it will give you the simplified version of the fraction. So G simplify is the simplified version of the fraction. So you know already how to use subs, simplify, and then later on you will learn how to use expansion or expand. Okay. Now, if I'm going to use f, now it will give you the same result. All right, now for the next problem, let's say we are going to expand 2x minus 3 quantity cube. Okay, now before that, now we will solve problem number 3 here. But before that, now we are going to initialize first our binomial. So in this case, I will write the binomial as a function. F now as your function of it. No need to write this now. So since you have initialized it a while ago, you don't need to initialize it again. But take note, we will be using the variables x and y. So meaning we are going to add y as a variable to our symbol to initialize that y is a variable for problem number 3. So take note of that. I actually copied now the first 3 lines and then paste it here. So now we are going to create a function, a binomial raised to a power of 3. Okay, that's a binomial raised to a power of 3. Now, if I'm going to display this binomial, so this is 2 minus x minus 2x minus 3y quantity cube. Now we are going to expand it by typing f.expand. So f.expand will expand the binomial. Okay. Not only binomial, if you are going to multiply 2 polynomial terms, so you are going to use expand so that it will expand on the polynomial. All right. Now we go to the next problem. Since we have problem number 4. This is problem number 4. solving. Okay, this is solving for problem number 4, or for number 4 problem. Let's start with creating a function here. So I will be using h, no, this time to represent my function. So this is 16 y to the 4th, 16 times y to the 4th minus 81 times x to the 4th. Okay. Now let's try to display the terms. So these are the terms. Now it's correctly displayed. After that, now we are going to factor out using, let's say, I will be, yes, s factor close parentheses. So that's how you factor the binomial. That's now the result of the fact. These are the factors of your binomial. Now for the last problem, we will be solving the last problem here. So we have variables a, b, c, and x. So I will copy the first 3 lines, and then I will initialize my variables, the symbols that I will be using. This is not a variable, but symbols that I will be using in my equation. So in this case, I will have a, b, c, x as my symbols. Now, to find the roots now of this function, we are going to equate this function no, to a function of k, removing 0. Okay, we will change 0 to k. This is now your k equals ax squared plus bx plus c. And I will use the solve function no, in Python to solve for the roots. So to solve for the roots, we can call on solve, put the function k, and then the variable x that you want to solve. Okay, take note, k there is the function and x is the variable that you want to solve. And it will give you a quadratic equation, a quadratic formula, I mean. So this is actually the quadratic formula that we have used now since then. Okay, this is the quadratic formula. That's how you use solve not to solve for the value of a variable. Okay, now let's proceed with our next topic. We go to calculus. In calculus, first, now we will discuss the limits. So we solve the limits using limit, and then you have the function. You have x approaches to a certain number, no? And for infinity, you're going to the right, so that is x approaches to infinity. Another one approaches to negative infinity. Now to take the derivative of the function, you can say diff, no? diff, that's the derivative of a function. For the second derivative of the function, now you can say diff of the function with respect to x, okay, to the second order. So that's the derivative of the function no, of variable x to the second order. That's how differentiation works in symbolic mathematics. Now, let's try to solve this one. We will be solving limits here. Okay, let's solve the first problem. Problem A. first, now we are going to express the function to the variable f. So we have x cubed minus 2x squared plus x. Now this is a fraction plus x all over x squared minus 1. Okay, that's how you write the function of x that will be represented by f. Now your f is equal to, okay, let me erase some of this part. So this will become x cubed minus 2x squared plus x all over x squared minus 1. So that's our f function that is represented by f. Function of x represented by f. So we will call it the function of x. Now, to display the limit, that's how you display the limit. Okay, erase now. We will use the function f instead. F now from x. So we have x approaches 1. So we have limit of f, x approaches 1. So take note, if you use limit with the capital letter L, now it will display the limit expression. So it will just display the math type set. But if you want to solve for the value of the limit, you use the lowercase limit. Okay, uppercase is used to display and lowercase is used to solve. So limit of f comma x comma 1 is the limit of your function when x approaches 1. That will give you 0. Okay, now if I'm going to change the value here, let's say, so it's 0 because maybe if you substitute 1 to the numerator will give you a value of 0. Let's try again to solve for problem number letter B problem. First, now we are going to represent the limit, the function to the variable g. So we have x cubed minus 9 times x all over x to the 4th minus 3 times x cubed minus x plus 3. Okay, now let's try to display first the function of x, the g of x. So this is my g of x. And then I will use limit to display the limit. The limit of your function g when x approaches, let's say x approaches 3 comma 3. So running the code will give you the limit expression. So we have limit of the function as x approaches 3. Now, if you want to solve the limit, you can say limit of g. Take note the lowercase limit as x approaches 3. Now it will give you 9 over 13. That's the limit. That's the value of the limit. All right. Now we go to more examples on limits. So for more examples, now let's solve the limit, this problem. Okay, I will label this as f of 1. So f of 1 equals 2. So I will create a function here, a fraction. We have square root of x plus 1 minus square root of 2. all over x squared minus 1. So let's try not to display the limit first, the function first. So this is square root of x plus 1 minus square root of 2 all over x squared minus 1. Then we will display the limit of f1 when x approaches, or let's say 1. So this is the problem that we are going to solve, right? Now to solve this problem, now we use the lowercase limit. So limit of f1 when x approaches 1, it will give you the value of the limit, which is equal to square root of 2 over 8. So that will be our first problem for the limits. Now we go to another problem. Let's label this as f2. Delete. Okay. f2 equals to, okay, I will create a fraction here. So we have here 5 raised to x minus 1 all over x raised to all over x. Okay, so we will display it first. So we have 5 raised to x minus 1 all over x. Now we are going to create a problem here. Let's say limit of f2 when x approaches 0. So we will display not the limit. Okay, this is the limit of 5 raised to x minus 1 all over x as x approaches 0. Now to solve for this, we are going to use the lowercase limit f of 2 comma x comma 0. Run the code and you have log of 5. Log means ln. Take note of that. A log in Python means natural logarithm. All right, now so proceed to the next problem. I'm sorry, I have not posted the problem, but instead of posting it, I just write it using the code. So we have here 3x cubed minus 3. So all over, we have 3 raised to x minus 3. Okay, now display it F3, run the code. So we have 3x cubed minus 3 all over 3 raised to x minus 3. Now we are going to display the limit now of f of 3 when x approaches, let's say, the value 1. So this is now the problem that we are going to solve. So to solve for the value of the limit, use lowercase limit of function of 3 f3 when x approaches 1. Run the code and you have 3 all over ln of 3. Take note, log in Python means natural logarithm. All right, proceed to the next problem. Now let's call this f4. f4 equals to, let me create the fraction here. So we have exp, it stands for exponential function, exp of x minus, let's say, exp of minus x all over, let's say, all over x. I'm actually thinking of the problem. So display it. So we have e raised to x minus e raised to minus x all over x. Now, if you are going to display the limit as x approaches, let's say, approaches 0, what will happen? Now, this is just the problem, I mean. Okay, now let me solve the limit, okay, by typing the lowercase limit of the function of f4 when x approaches 0. Run the code. Charan, the value will be 2. So if you will notice, no, you will use a L'Hopital's rule in this problem. Okay, that's 2. That's the limit. Now proceed to the next problem. Let's try f of 5. Okay, so let me create a fraction first. So we have the same, no, the exponential function of x minus 1 all over x squared. So let's display this first. So we have e raised to x minus 1 all over x squared. And then we will display the limit, as x approaches, let's say 0. So this is a limit of e raised to x minus 1 all over x squared as x approaches 0. To solve for that value, we use the lowercase limit of f5, and then x approaches 0. That's the value of your limit, equal to infinite. Infinite. All right. Now proceed to the last problem. This time we will use the cosine function. Let's say 1 minus 2 times cosine of, let's say, cosine of x all over pi minus 3 times x. Let's display this first. Type fx, f6, I mean. So this is now your f of 6. Okay, the 6 formula. Now we will display the limit as x approaches, let's say x approaches pi over 3. So let's see what happened. So this is now your limit. And to solve for this limit, now we will be using the lowercase limit. So we have limit of f6 as x approaches pi over 3. Run the code. There you go. That would be the value of our limit. Okay, I hope you've learned something about limits. Now we will proceed with differentiation. Okay, let's try to take the derivative of 4 problems shown now on the screen. Okay, let's try to take the derivative of this. Okay, let's start with our first problem. This is problems on differentiation. Now, differential calculus will be easier now if you know how to use Python. Same is true with other mathematics subjects like integral calculus, differential equation, and in your current subject, the advanced engineering mathematics. All right, now let's solve problem number 1. So I have here y is equals to the exponential function of x cubed. You can say exp x cubed multiplied by, okay, x raised to 7. This is 7. Now let's display it first. So this is now your x raised to 7 multiplied by e raised to x cubed. Now to display the derivative, this is how you use to display the derivative. So derivative y. The same is true with the uppercase limit. That's how you display the limit. So in this case, it will give you d over dx, means the derivative of x raised to 7 times e raised to x cubed. Now to solve for the derivative, we use diff. Okay, diff of y with respect to the variable x, or you may say diff of y only. Okay, that's how you solve for the differential or the derivative of a function. Now let's try another problem. Now, in this lecture, now you are going to learn how to write equations as well. Not only solving equation, but you will learn also how to write a symbolic mathematical equation. So we have here y equals to the square root of 4 times x minus 9 multiplied by, we can say, log or ln. So the same, log or ln will work here. So ln of x to the 4th. So display it, it will become log. So when you type ln, it will automatically convert it to log. Now, to solve for the derivative, we use derivative of y. So display the derivative. No, that's the derivative of the product. So easy, right? So if you know this, since you were on your first year, calculus will be easy. Let's have the next problem, or the third problem. Let's say y equals to e raised to x. You can say exp raised to x multiplied by 7 times x minus 1 raised to 1/3. So we can say raised to 1/3. Now take a look at this one. If you will display this, it will give you the power of 0.3333. Okay. Now, if you want to take, let's display the derivative of y with respect to x. So this is the derivative of this function with respect to x. Now, let's solve the value or the derivative, by using the diff y. So diff y is the derivative of your function. Okay, press run, and there you go. You have now the derivative of the function. Okay, down to the last problem in differentiation. Let's say I have here the fourth problem. So y equals to the square root of x multiplied by ln of x. You can say ln of x. And then we are going to display the derivative of y with respect to x. And then take the derivative of the product. So run, that's the derivative of the product. So ln x all over 2 times square root of x plus 1 over square root of x. All right. Now we go to the next slide. Integration. Under calculus, we have integration. So integration is just the reverse of differentiation. Don't forget to put C in your integral, but in Python, C is not written here. Let's try. So for the first problem on integration, let's solve problem A. Now take note, now integration, we use integrate, not int, okay? Int is for integer. So in this case, we will be using integrate. So first we will write the function y equals square root of 5 plus 2x. And then we are going to display the integral of y. So let's try. So this is now the integral of square root of 2x plus 5 dx. Now, if you want to solve for the integral, So don't use int because int is wrong. So if you put x, still wrong. Instead of int, we use the function integrate. So int is used in MATLAB, not Python. So we will change this to integrate. So integrate. So y with respect to x, now you have your integral. Take note, c is lacking here. So c is lacking. So let me zoom in the lines. Okay, now we solve for the next problem. Don't forget to write plus c in your equation. So let's say I have here problem number 2. Let's create a function of x. Now y equals to x all over x squared plus 1. And then we will display the function. So this is, so okay, now let's assume limits now so that we can practice how to use limits. So in this case, x is from 0 to, let's say, 10. So to write the limit, so you can say integrate. This is to display the integral with limits. So integrate, no, integrate, integral, I mean. So integral is to display. Integrate is to solve. So integral of y with limits. Now this is how you put limits. Now x, so you have your parentheses, then x from 0 to the value of 10. That's how you put your, what do you call that? Okay, by the way, so here the syntax error for x raised to the power of 2. So you don't need, we don't use caret here, but instead double asterisk. So this is double asterisk. So run the code. There you go. You have beautiful integral from 0 to 10 of x over x squared plus 1. Now, to solve this problem, you use the lowercase integrate y and then put the limits from x equals 0 to 10. There you go. You have ln of 101 all over 2. So take note of using the limits. All right. Now we are going to solve the third problem. Let me introduce y to your function of x equals to x times open close parentheses 3x squared minus 4 all to the power of 5. So double asterisk 5. And then we are going to display the integral. Let's say integral of y. So we have beautiful integral of y. So then integrate to solve the value of the integral. So integrate with respect to x. It is assumed that the integral of that will be this, these terms. Okay. Now that's easy. Now down to the last problem in integral calculus. Okay, now for the last problem in integral calculus. Okay, let y equals to, we have this fraction, open parentheses 3x cubed, close parentheses, all over. We have x to the 4th square root of x to the 4th the 4. plus 4. So we are going to integrate. Okay, integrate y, display it, the integral. Oh, there you go, the beautiful integral. Okay. So that is the integral of 3x cubed all over square root of x to the fourth plus 4. Then to solve for the integral, we have to integrate y. So don't forget to add plus c. Okay. So that's it for integral calculus. Now we proceed to differential equation. Now in differential equation, this is how you are going to define your variable as a function. So example, if you want to define f as a function of x, you can say f here no is equals to symbols no, and then we have CLS means class of function. So you are going to define f here as a function. So let's try. Now, if you put f of x, now it will display a function of f with respect to x. Now let's try. Now, if you want to take the derivative of the function of x, you can just say f of x dot differential. Take note, we already know how to use the differential. Differential of the variable, in that case, that's x, and the order. Like for example, if you want second order, you may put 2 here. And then to create your differential equation using, okay, to create your differential equation, we will be using this equation. So I don't know if you can see here, but later on, no, I will be coding this so that now you will see how to use the differential equations, how to create the beautiful differential equation. Now to solve the differential equation, we use dsolve. Just like in MATLAB, we also use dsolve. Okay, now we go to the coding part. Okay, first now we are going to load again SymPy. So a module of SymPy. So from SymPy, we are going to import asterisk. We are going to solve for the problem shown above. Okay, now first, now we are going to define the function f. We have f equals to symbols. Then we have single quote f. And then we are going to change f to a function. We are going to declare it as a function. Let's try. So by typing f of x, no, you will see now your beautiful equation f as a function of x. Now, if you want to take the derivative, let's say, let's take the derivative. I want to take the differential of f of x. Let's say f of x times diff. Okay, let's say x. Okay, that's the first derivative of fx. Now you will see the derivative of fx with respect to x. All right. Now let's try again. If you use, if you will take the second derivative, you can say x comma 2. That's the second derivative of your f of x. That's how you use your differential in x. Now, let's create a differential equation. So by typing equation, that's how you create differential equation, open, close parentheses. First, we are going to create f double prime. So f double prime is the second derivative of fx. So we can say f of x dot diff times diff x to the second derivative minus 2 times f of x prime. So we can say f of x dot diff. This is your f of x prime plus f of x equals to 0. So instead of equals, we use comma. Not equals to sign x, I mean. So instead of equals to sign x, we use comma. So this is now your differential equation, okay, of second order. Okay, it's the same. That's our differential equation of second order. Now we are going to solve the differential equation using dsolve. So you will write your dE, okay, followed by your function of x that you want to solve, okay, and then you have your differential equation with a constant of C1 and C2, because you notice that we don't have initial values. Okay, if you have initial conditions, now it is easier to solve using Python programming using SymPy module. Okay, now let's proceed to the next problem. This time, now we will be solving problems now shown there. So here we are going to solve the ordinary differential equation, but this time we are going to use the initial condition. Okay, now let's start our initial condition problem. So let's start with problem number 1. Take note, no, before you start, you have to initialize your variable. In this case, instead of f, I will be using y. So symbols, of course, this is y, comma, plus equals function. So I declare y as a function. And then I also use the symbol t, because no, t will be used instead of x. So y is a function, t is a symbol. Now you can write y of t, and it will give you a function of y with respect to time. Okay, y of t. Right, now we are going to create a differential equation of the problem of A. So we have here equation. Okay, the second derivative is yt dot diff. Let's say diff x comma 2, because that's the second derivative, plus y prime t. So you can say yt dot diff t. Oh, by the way, we are using t, not x. All right. So t plus, let's say, plus 3 times yt equals to 0. Instead of equals, you use comma. So comma 0. So take note, this is the differential equation. If you want to display the differential equation, you can say display diff equation. So it will give you the display of the differential equation. That's the differential equation. Oh, by the way, no, instead of f, no, we will be using, look at that. So f, no, it's actually y. So again, run the code. That's 3yt. Okay, so it's fixed. Now, after displaying, we are going to solve using dsolve, okay, of y, of your differential equation, okay, as a function of y, uh, yt, and then we are going to use the initial condition. So ICS now is the initial condition. We have curly braces. Then we are going to assume y0, that's y0 colon 1, since y0 is equals to 1, and then y prime 0, you can write y prime 0 as yt dot differential diff of x. Then we are going to substitute, okay, that diff of t. Then we are going to substitute t, not x, okay, by 0 equals to 2. By the way, what is wrong? Okay, x. Oh, I forgot to substitute. So t. Now that is the value of the differential equation. Okay, without a constant, of course, because we substituted the initial condition. We included the initial condition. Now let's try the second problem. Okay, I will copy this. We don't need to copy that because it is declared already. Now we will be solving problem number 2. Okay, now let's have differential equation equals EQ, or equation. That's the second derivative of yt. So we can say yt dot diff x comma 2. That's how we represent the derivative of the function. Okay, plus we have 2 times yt, okay, times the derivative of the function of t. Okay, by the way, this is t, okay, because I'm used to x. No? And the last one will be plus 4 yt, comma 0. That is equal to 0. Now, if you are going to display the function, okay, you type display diff eq, differential equation. Run the code. Okay, run the code. We have our differential equation. Okay, now since we have our differential equation, let's solve the differential equation using the solve of the differential equation as a function of yt. Now let's say yt, comma, with an initial condition ICS equals to, enclose it with curly braces. We have y prime, y0, we have y0 colon, okay, equals 1, comma, that's the first one. Then we have y prime 0. Y prime 0 is represented by yt dot diff with respect to t, and then substitute t with 0, colon, value is 2. So that's it for the differential equation, the solution to the differential equation of problem number 2. Now let's solve for the last problem here. I think this will be the last problem. Try to practice now the problems that we haven't solved here. Okay, now we have differential. You can pause the video if you want. Now we have the differential equation for the problem number 3 of EQ. We have the second derivative of yt dot diff, open close parenthesis, comma, x, comma 2. That's the second derivative, plus yt, derivative of yt, we can say yt dot diff x, t I mean, okay, equal to comma sine t. So equal means comma. Then we display the differential equation. Okay, display the differential equation, run the code. That's your differential. Oh, where is it? This is t instead of x. Okay, this is t instead of x because we are using t. Again, run the code. So that's it. So be careful when you use your variable. Now we need to solve this differential equation, and then including the initial values. So we have dissolve this equation, comma, as a function of yt, comma, ICS, that is initial conditions, open curly brace, y0 under colon 1, and then we have y prime 0, that's yt dot diff t, and then we are going to subs, okay, we are going to substitute t to 0, the value is 2. Run the code, then you have your nice and beautiful differential solution to the differential equation. All right. That's it for the differential equation. So I hope now you've learned something now from this topic on differential equation. Now we go to the last and final topic, the Laplace transform. Okay, we still have a lot now to discuss in SymPy, but we will reserve that for our future topic. We will proceed first to the Laplace transform. So recall that the Laplace transform of ft is just the integral from 0 to infinity of your function of f of your ft multiplied by e raised to minus t minus st dt. Now in SymPy, we use Laplace transform now to solve for the Laplace transform. So Laplace transform function, that's your function, comma t, comma s, no condition equals true. Okay, that's for the Laplace transform. Below is the inverse Laplace transform. Okay, now we go to the coding part. So let's start by loading SymPy module and then initializing the print output. So we have init printing. Okay, and we will be declaring the variables that we'll be using. In this case, we will be using t and s. That's our symbols, symbolic math symbols. Okay, we have symbols ts. Okay, that's it. Now that's how we define our symbols in SymPy. Now let's try the Dirac delta function. So we say, how do we represent Dirac delta function? So Dirac delta function now can be represented by f is equals to Dirac delta. So you can say Dirac delta as a function of time. Now, if you want to view the symbol for Dirac delta, that's it. Now that's the symbol for the Dirac delta. So I will be using display here instead of just typing f, because now we will take the Laplace transform of this. So we have Laplace transform of your function of f t to s, comma, no cons. No cons means no condition, true. So display, run the code, and there you go. The Dirac delta, the Laplace transform is 1 minus the unit step of 0. Okay, minus the unit step 0. I don't know. That's the initial state, no, of your Dirac delta. Now let's try to delay it by 2 units. What will be the result? What will be the result if we delay it by 2 units? So that will be the shifted Dirac delta function, shifted by 2 units. So the result will be e raised to minus 2s. So that's it for the Dirac delta function. Now we go to the very famous Heaviside function, or commonly known as the unit step function. Now, what is the symbol for this unit step function? So let's declare f equals to Heaviside as a function of time. And then we will display f. Let's say display the Heaviside function. So take a look at the symbol for Heaviside. So you can see the symbol is theta. Okay. So we will be using theta in this SymPy programming to represent Heaviside function. Then we take the Laplace transform of the Heaviside function. Okay, we have yes, no, cons equals true. Run the code, and there you go. You have 1 over s is the Laplace transform of the Heaviside function. If we are going to shift it by 7 units, that will become e raised to minus 7s all over s. Now, let's make the Laplace transform easier or shorter to run, shorter to type. This time we are going to create functions. Okay, we are going to create functions. Later on, we will discuss more on the function. To create a function, we use diff, and we will represent Laplace transform as L. Okay, and the argument is f. So if you type L and the argument of f, it will return this Laplace transform. It will return this Laplace transform. So meaning to say, instead of writing Laplace transform, I will just use L instead of Laplace transform. That's how it works, the function. So instead of using that, I will use LF. Okay, run the code, and then let's try the Laplace transform using L and not the Laplace transform, so that it is easier for us to deal with longer codes. Okay, then we say, what is the Laplace transform of the function of t raised to a certain number? Let's say t raised to n. So assuming I have here f equals to t to the power of 2, let's display this one first. Display f, run the code. Oh, we have t squared. Now, instead of Laplace, I will just type L and then f. Oh, so that's easy, right? And then I have now the Laplace transform of my function of t, which is 2 all over s cubed. Now, if I'm going to change this to the power of 5, this will become 120 all over s raised to 6. Okay, let's try one more. This time we go to the exponential function. Exponential function. Okay, change to exponential function. Okay, exponential function, let's say f equals to e raised to 4t. We will display it first and then take the Laplace transform. Okay, display, and then the Laplace transform is LF. Run the code. Oh, that's it. No, that's 1 all over s minus 4. That's the Laplace transform of your e raised to 4t. Now we go to the next problem. This time we go to the sinusoidal function. Let's start with f equals to 4 sine of, let's say, negative 2t, or simply 2t only. Now we are going to display this. And then take the Laplace transform with. So we have 4 sine 2t, that's 8 all over s squared plus 4. All right, now we go to, let's try another function. Let's say cosine function. Shall we say 5 times cosine of, let's say, 3 times t. So we will display f first, and then we will take the Laplace transform of f. So we have 5 cosine 3t is just 5s all over s squared plus 9. Now we go to the hyperbolic function. Let's start with sine hyperbolic. So we have 3 sine hyperbolic of 4 times t. Okay. First, we will display it. And then we are going to take the Laplace transform, LF, run the code. We have now your hyperbolic function of sine 4t. So it will take a while since this is a hyperbolic function. So the result will be 12 all over s squared minus 16. All right. Now we go to shifting. Okay, let's say first a shifting property. So in this first shifting property, take note that the function is multiplied by the exponential function. Let's say I have here the function sine 2t, and I will multiply that to an exponential function, e raised to 2 times t. Let's display this first. Display the function, and then take the Laplace transform. Run, and there you go. That's the Laplace transform of the shifted sinusoidal function. Okay. Now we go to the multiplication by t, or commonly called as derivative of Laplace transform of LT. Derivative of Laplace transform. So that is function multiplied by t. So we have t multiplied by the cosine of, let's say, 3t. So first we will display it, and then after that we are going to take the Laplace transform. So that's it. So t cosine 3t is just s squared minus 9 all over s squared plus 9 quantity squared. That's the Laplace transform of the function. So derivative. Now we go to the division by t. So we have the integral of Laplace transform, or LT. So when the function is divided by t, let's say sine of 2 times t divided by t. Oh, what's this? Let's display f first, and then we are going to take the Laplace transform of f. All right, so sine 2t times over t is just negative arctangent of s over 2 plus pi over 2. That's the division by t, or the integral of Laplace transform. Now we go to the second shifting theorem. Second shifting theorem, let's say sine t minus pi multiplied by the Heaviside function of t minus pi. Let's try if this will work with sine function. So we are going to display it, and then we are going to take the Laplace transform. All right, so there you go. That's the displayed function. And oh, it will take a while. So let's just wait now for the Laplace transform of the Heaviside function. Oh, there you go. It's the same. It's just the Laplace transform. So meaning to say, it cannot solve this problem. Now let's just change this one. Instead of sine, let's just use the exponential function. So, oh, that's the exponential function, and that's the Laplace transform of the exponential function in second shifting principles. All right. Now we go to the inverse Laplace transformation. Let's start by defining. We will define the INVL, so inverse Laplace transform of capital F. That's your argument. So it will return. Okay, it will return the inverse Laplace transform. Okay, of F, comma T, comma S, comma no condition true. All right, let's try the basic inverse Laplace transform. Run it first. Don't forget to run it. And then let's say F equals 1 over S minus 4. Okay, and then take the INVL. Okay, first we are going to display it and take the INVL F. Display. Oh, what happened here? Oh, this is S. Okay, let me debug this one first. So this is the problem when you wrongly typed, you know, the conditions or the argument here. In this case, no. So I have seen it. You have to interchange S and T. Since this is the inverse Laplace transform, it will change S to T. So that's it. I'll run again, and you have your answer. So take note of theta T. That is actually your Heaviside or your unit step function. 1 over S minus 4. That is e raised to 4t u sub t. But in that case, no, in SymPy, it will give you theta t. So let's try this one. Let's have 3s. Okay, let's create a fraction here. 3s minus 1 all over. I'm thinking of using buka-buka. So using s squared minus 2s plus, let's say, 10. So we are going to display the fraction first. Okay. That's it, no? So in this fraction, we will be using the 4B method. So can you still recall your buka-buka and bika-bika binastos method? So this is buka-buka, bika-bika method, or shall we say divide and conquer method. Okay, this is the inverse Laplace transform. That's it. Now that's the inverse Laplace transform of buka-buka, bika-bika problem. So theta t is actually your unit step function here. Never mind. No, you can ignore it. It means that your function will have a value from 0 up to positive infinity. Now we go to partial fractions. So let's have a fraction here, and then we will resolve the fraction using partial fractions. So I have here s squared minus s plus 1. Okay. And then I have the denominator s times s minus 2 times s minus 3. And then we are going to display f. Let's try. Oh, what is missing? Okay, I found it. So we are missing, okay, slash. Okay, now that's your fraction. Now we are going to resolve the partial fraction of this fraction. So instead, now we will be displaying f dot apart. Apart is actually converting fraction into its component fraction. Okay, it will create partial fractions from the original fraction. So that's a part. So that's it for your partial fraction. Okay, so it is easier now if we have lectured this before the exam. So we have inverse Laplace transform of f. Now we have the function of t. That's the inverse Laplace transform of your partial fraction. All right. So let's have some more problems in partial fractions. Okay, we have here f equals to s squared minus 4 all over, let's say, s minus 2, or let's say 3 to the power of 4 to the power of 2, meaning s minus 3 squared times s minus 1. So this is a repeated linear factors. So let's display this one. So you can see the s minus 3 is repeated. Now, if we will display the equivalent partial fraction, you can say f apart, and then it will display the equivalent partial fraction. Now let's try. Let's try to take the inverse Laplace transform. I know that Python will be slow, in taking the inverse Laplace transform of a repeated, especially when the denominator have a power, or that is a repeated linear factors. Okay, be patient. Wait for a few seconds now. So this will take a while because of the structure of your Laplace transform, and it depends on the speed of your computer and your internet. So there are a lot of factors here. But the main factor is it depends on the function of s that you want to take the Laplace transform. So I give up. I will change the problem. Before that, I will run it again. Okay. And then I will change the problem here, and I will delete this one. Okay, let's try. Okay, that's it. Still the same if you deleted the line, the apart fraction. Okay, let's stress our patience. Okay. I give up. All right, I give up. So instead of using s minus 3, I will just use s squared. Okay, s squared. So let's try. There you go. Okay, so it depends on the terms in your denominator. So this one is more easier. Okay, that's it for the partial fraction. So what will be our next topic? This is the last topic actually of SymPy, partial fraction. Okay, this is the end of our lecture. So what did we do? We use symbolic mathematics, using Python, SymPy to solve problems in algebra, problems in calculus, in differential equations, and in Laplace transform. All right. That's it for today, and I will see you in the next meeting.